The United States has lost more than 8 million hectares of farmland in just 5 years. But instead of using the remaining fields only for crops, people are now building massive wind farms on top of them. From transporting turbine blades dozens of meters long, excavating concrete foundations, erecting steel towers, and installing nacelles to laying underground cables that feed electricity into the national grid, these wind machines are turning farmland into a two-layered system. But is this a new source of income that helps farmers keep their land, or a quiet invasion that is reshaping rural America? Join Terran Works as we explore it in today's video. Did you know that to power modern cities, Americans are not only turning to deserts or distant offshore waters, but are also erecting wind turbines taller than the Statue of Liberty right in the middle of crop fields and grazing lands? Having grown rapidly since the 1980s and 1990s, this is a model that combines wind power with agriculture, allowing a single piece of land to produce both food and energy. According to the USDA, between 2012 and 2020, most new rural wind turbines were installed on cropland or pasture land. In the Midwest alone, about 94% of turbine locations were on cropland. This has become even more important as the United States lost more than 8 million hectares of farmland in just 5 years. Roscoe Wind Farm in Texas is a typical example. Completed in 2009 with 627 turbines spread across nearly 40,000 hectares, the project shows how a field can continue producing agricultural goods while also becoming a giant power plant. But behind that picture are many controversies. Turbines can alter the landscape, raise concerns about noise, flickering shadows, transmission lines, and divisions between landowners who receive lease payments and nearby households who live around the project. So why, despite all these controversies, is farmland still considered one of the most suitable places for wind power? The answer lies in the very nature of open fields. They are wide, unobstructed, have steady winds, and provide enough space for turbines to stand far apart without making agriculture disappear. So, how are these massive wind farms on agricultural land actually built? Before wind can be turned into electricity, a turbine must go through one of the most complex, oversized, and overweight transportation operations in the modern energy industry. The process begins at the factory, where steel tower sections, the nacelle, the hub, and the blades are inspected, marked, and separated into giant cargo units. Then, the logistics team surveys the entire route: which bridges can withstand the load, which turns are wide enough, which power lines need to be lifted, and which road signs must be temporarily removed. Only when the route is approved do the oversized trailers begin leaving the factory or transit port, often with escort vehicles driving in front and behind to warn traffic. On the way to the wind farm, the convoy has to move slowly across highways, small towns, and rural roads that are normally used to tractors or trucks carrying agricultural goods. Blades dozens of meters long require specialized vehicles capable of adjusting their angle to pass through narrow turns, while the nacelle and tower sections, weighing from tens to hundreds of tons, require roads strong enough and bridges with sufficient load capacity. When the components arrive at the construction site, each part is lowered into the staging area and arranged in the correct order for assembly. According to NREL, the transportation cost alone for onshore wind turbines can account for about $194 per kilowatt. For a 3-megawatt turbine, transportation and logistics can amount to more than $500,000. After the transportation journey, the turbines still cannot be erected immediately. First, the construction site must create a concrete foundation, the base that keeps the entire structure, hundreds of meters tall, standing firmly against strong winds. Workers position the tower location using GPS, strip away about 30-50 centimeters of topsoil, and then excavate a foundation pit 2 to 4 meters deep and 15 to 25 meters in diameter. The bottom of the pit is leveled, compacted, and checked for elevation to ensure it can bear the load. Next, a reinforcing steel cage weighing around 20 to 60 tons is installed inside the foundation pit. At the center, a massive anchor bolt system is positioned with precision so it can later connect to the tower body. After that, concrete is poured continuously to form one seamless block. Each modern onshore turbine foundation may require 300 to 700 cubic meters of concrete, equivalent to 40 to 90 concrete mixer trucks with an 8 cubic meter capacity. Once the concrete reaches the required strength, the surrounding area is backfilled, leaving only the round base and the maintenance access path exposed. Once the concrete foundation has reached the required strength, the construction site enters its most spectacular stage, erecting the turbine. First, a large crawler crane is moved into position. Then each steel tower section is lifted, placed precisely onto the anchor bolt system, and tightened with specialized tensioning equipment. For new turbines installed in the United States in 2023, the average hub height reached about 103.4 meters, while the average rotor diameter was around 133.8 meters, showing the enormous scale of each installation. After the tower body is completed, the nacelle, the heart of the turbine, is lifted to the top of the tower. Inside it are the generator, drivetrain, brake, wind sensors, and control system that allow the turbine to turn toward the wind. A modern onshore nacelle can weigh around 50 to 160 tons, so even a slight shift in wind or a small operational error can make the lifting process risky. Finally, come the rotor and the 3 blades. The blades can be installed one by one onto the hub, or pre-assembled into a full rotor on the ground and then lifted into place. This step usually takes place only when the wind is low and stable enough, because the entire rotor behaves like a giant sail in the air. In the middle of fields once familiar with tractors and silos, a structure more than 100 meters tall slowly rises into the sky. After the turbine is erected, it still cannot supply electricity to a city immediately. The electricity generated inside the nacelle is carried down to the base of the tower through cables, then travels through underground cables or internal collection lines to the wind farm substation. Put simply, each turbine works like an individual generator, while the substation is where all that electricity is collected before being sent into the larger power grid. There, the electricity is stepped up to a higher voltage so it can be transmitted over long distances with less loss. Engineers then check the control system, wind sensors, vibration sensors, temperature, rotational speed, and the automatic shutdown mechanism in case of faults. Only when all parameters meet the required standards is the turbine connected to the regional grid. But this is also one of the biggest bottlenecks for wind power in the United States. Many agricultural regions have excellent wind resources, but are located far from cities and industrial zones. So additional transmission lines are needed to carry the electricity over long distances. By the end of 2023, about 366 gigawatts of wind power capacity in the United States was still waiting for grid connection. This shows that the challenge is not only generating electricity, but also delivering that electricity to where it is needed. Once the electricity from the turbines has been collected at the substation and fed into the power grid, the story no longer stops at engineering. At this point, the bigger question is, how does this model actually operate on a real farm field? Iowa is one of the clearest examples. It is a state known for corn and soybeans, with wide open plains and few obstacles, exactly the kind of terrain wind power needs. In Iowa's cornfields, turbines are not placed close together like utility poles. Instead, they stand hundreds of meters apart, so they do not block one another's wind flow. The land between the towers remains wide enough for tractors, planters, sprayers, and harvesters to operate throughout the growing season. The area directly occupied is mainly limited to the turbine foundation, access roads, and maintenance zones. Most of the field continues to grow corn or soybeans. As a result, the same piece of land can create two streams of value: crops rising from the soil and electricity generated from the wind above. This is especially impressive because Iowa is not a small agricultural region. The state is often among the leading producers of corn and soybeans in the United States. In 2024, Iowa harvested about 2.6 billion bushels of corn and more than 600 million bushels of soybeans, showing that turbines have not erased the state's agricultural role. On the contrary, they stand in the middle of one of America's largest food-producing machines. That is why Iowa has become a symbol of agricultural wind power. In 2024, about 63% of Iowa's net electricity came from wind, while the fields beneath continued to produce billions of bushels of crops each year. Unlike in the United States, where wind power often slips in among crop fields, in Australia this model is more closely tied to vast grazing lands. Across immense pastures, turbines can be built on sheep farming land without making the livestock disappear. Below, sheep still graze, move along internal roads, and are managed according to the grazing season. Above, giant blades quietly turn wind into electricity. This is especially well suited to Australia, where the sheep industry operates on a very large scale. The country has had more than 70 million sheep in recent years, making it one of the world's most important producers of wool and sheep meat. Australia's wool industry alone generates billions of Australian dollars in export value each year, while mutton and lamb are also major agricultural export products. So when wind power appears on grazing land, it does not replace the sheep. Instead, it adds a new source of income for landowners. McIntyre Wind Farm in Queensland is a prominent example. The project has a capacity of about 1,026 megawatts, includes 180 turbines, and stretches across roughly 36,000 hectares of agricultural land. Major construction was completed in 2025, and the project is now in the testing and grid connection phase as it moves toward full operation. Once completed, it is expected to supply electricity to around 700,000 Queensland households. This is a very clear image of two-layer agriculture. The ground continues to produce wool, meat, and pasture, while the sky above generates energy. Economic benefit is one of the main reasons many farmers accept wind turbines on their land. Agriculture has always depended on weather, crop prices, fertilizer costs, fuel prices, and interest rates. Even a good harvest can turn into a failure if the market moves in the wrong direction. In that context, land lease payments from turbines become a more stable source of income, often lasting 20 to 30 years and not directly tied to crop yields. In the United States, in 2024 alone, wind and solar projects contributed about $4 billion in local taxes, state taxes, and land lease payments to rural communities. This money can support schools, roads, fire departments, public services, and county budgets. Wind power also creates new jobs. The U.S. Bureau of Labor Statistics projects that employment for wind turbine technicians will grow by about 50% from 2024 to 2034. Wind power on farmland sounds like an ideal solution, but behind it are many controversies. The first is the landscape. A modern turbine can stand more than 100 meters tall, even taller than the Statue of Liberty. So for opponents, it is not just an energy device, but an industrial structure that changes the rural skyline. The second issue is the impact on the community. Noise, flickering shadows, nighttime warning lights, construction trucks, internal roads, and transmission lines. Although these impacts can be reduced through safe setback distances and good planning, conflicts still arise when landowners with turbines receive lease payments, while their neighbors only experience the effects. Another major limitation is the power grid. By the end of 2023, about 366 gigawatts of wind power capacity in the United States was still waiting for transmission connection. And after 25 to 30 years of operation, turbines must be upgraded or dismantled. If the contract does not clearly define the cost of restoring the land, today's clean energy can become tomorrow's dispute. The future of wind power on farmland is not only about how many more turbines are built, but about how they are built more fairly. Electricity demand in the United States is rising again after years of stagnation. The EIA says national electricity consumption has increased by an average of 2.1% per year over the past 5 years, with data centers being one of the major drivers. Because of that, windy rural regions will continue to attract attention. But the new model cannot simply place turbines on land and call it green development. The benefits need to be shared more widely, not only with landowners who host turbines, but also with the communities affected by transmission lines, noise, or changes to the landscape. Technically, future turbines will be taller, more efficient, and will require fewer towers to generate the same amount of electricity. By the end of 2023, the United States had installed about 150,500 megawatts of onshore wind power. If the land is protected, contracts are transparent, and communities have a real voice, two-layer agriculture could become a powerful model of the 21st century, a field that feeds people while also powering the modern economy. The world is entering the era of renewable energy, where solar and wind power are taking up an increasingly large share of global electricity generation. Each year, humanity consumes more than 27,000 terawatt-hours of electricity, an enormous figure equivalent to trillions of kilowatt-hours, and this demand continues to grow. In Europe alone, renewable energy accounted for over 40% of total electricity generation in 2023. But this rapid expansion comes with a paradox that modern power systems have yet to fully solve. Solar power is only available during the day, and wind power only when the wind blows, while electricity demand fluctuates constantly from hour to hour, even minute to minute. As a result, there are times of massive oversupply and others of severe shortages. This paradox places enormous pressure on the power grid. Without effective storage solutions, a significant portion of the tens of thousands of terawatt-hours of electricity produced each year would be wasted. Yet storing electricity at this scale is far from simple. Lithium batteries can do it, but the costs are extremely high, and scaling them to a national level is nearly impossible. And that's when engineers turn back to a solution that seems almost traditional, yet remains the most effective: using water. From this idea, the concept of a natural battery was born, and Limern is its answer on a massive scale. Built deep within the majestic Alps of Switzerland, Limern is one of the most ambitious large-scale energy storage systems ever created by humans. Instead of generating electricity in the traditional way, this facility operates like a giant battery, capable of storing up to 34 gigawatt-hours of energy by pumping water uphill and releasing it when needed. When the grid has excess energy, water is pumped from the lower Limern Reservoir up to Lake Mutsee at an elevation of over 2,400 meters. When demand rises, this water rushes back down through turbines, generating electricity almost instantly with an efficiency of around 75 to 80%. Behind this system is the energy company Axpo, working alongside dozens of leading engineering contractors across Europe, with more than 1,000 engineers and workers operating continuously under harsh conditions for nearly a decade. Construction began in 2008 and was completed between 2016 and 2017, with total investment exceeding $2.3 billion. At the core of the entire system is a height difference of up to 630 meters between the two reservoirs, a gap large enough to generate immense potential energy, effectively turning the entire mountain into a true natural battery. But what truly sets Limern apart is not just its scale, but its role. This is not a conventional power plant. It is part of Switzerland's long-term strategy to become a battery hub for Europe, helping to balance the electrical grid across the region. But to turn an entire mountain into a battery, the first challenge wasn't the technology. It was simply getting people and machinery up there. The Limern construction site wasn't located on flat ground. It was suspended at an altitude of over 2,000 meters in the Alps, in a place that was almost completely isolated, with no road access. This made logistics one of the most difficult problems of the entire project. Instead of trucks or conventional transport routes, engineers had to build an industrial cable car system nearly 4 kilometers long, spanning steep mountain cliffs. This system could carry loads of up to 20 to 30 tons per trip, including drilling machines, steel, concrete, and all the necessary construction materials. In areas where even cable cars couldn't reach, helicopters were deployed. hundreds of flights were carried out to transport workers and equipment into position. In many cases, workers had to be lowered onto near vertical slopes, like professional climbers approaching a dangerous rock face. At the mountaintop, a temporary city was built, where hundreds of workers lived and worked continuously under freezing temperatures, low oxygen levels, and highly unpredictable weather conditions. The logistics system alone cost tens of millions of dollars and took years of preparation before construction could officially begin. But all of that was only the beginning, because the real challenge didn't lie outside. It lay deep within the mountain itself. Inside the Alps lies an extremely hard layer of granite, with compressive strength exceeding 200 to 250 megapascals, making conventional excavation methods nearly useless. To carve a path into the mountain, engineers had to rely on controlled drilling and blasting, a technique that requires near-perfect precision. Each day, modern hydraulic drilling rigs create dozens to hundreds of boreholes, ranging from a few meters to over 10 meters deep, arranged according to a meticulously calculated pattern down to the centimeter. Once drilling is complete, explosives are loaded into each hole in layers, interspersed with stemming materials to direct the blast energy. Electronic detonation systems allow explosions to occur in sequence with delays of just a few milliseconds, creating a chain reaction fracturing effect that controls the direction of rock breakage and minimizes the risk of collapse. In a single blast, hundreds of kilograms of explosives may be used, releasing enough energy to shatter massive rock layers within seconds. After each detonation, thousands to tens of thousands of tons of broken rock are produced, quickly collected and transported out by specialized trucks operating continuously in cycles. This process is repeated hundreds, even thousands of times, gradually expanding the space deep within the mountain. After hundreds, even thousands of drilling and blasting cycles, engineers carved out a tunnel system stretching over 20 kilometers deep inside the mountain. A complex network, comparable in length to an entire underground city. But these are far more than simple passageways. Each tunnel is designed as part of a multifunctional infrastructure system, serving not only for equipment transport, but also integrating high-pressure water pipelines, electrical cables, and technical systems. Some sections reach diameters of 8 to 10 meters, large enough for heavy-duty trucks to operate continuously inside, while smaller technical tunnels are densely arranged to connect every part of the facility. The total volume of excavated rock exceeds millions of tons, creating a vast underground space equivalent to around 30 football fields, effectively transforming the mountain's interior into a nearly self-contained engineering complex, completely hidden beneath hundreds of meters of solid rock. Every tunnel is reinforced with reinforced concrete and modern rock anchoring systems, enabling them to withstand immense pressure from the surrounding rock. Pressures that can reach tens of megapascals. Construction tolerances are controlled down to the centimeter, as even a minor deviation could affect the entire system. Beyond serving as connections, this tunnel network functions as the circulatory system of the entire facility, continuously transporting water, energy, and data between different components, from reservoirs and pressure pipelines to turbine stations and power transmission systems. At the heart of the system lies the main turbine hall, a vast space carved directly into solid granite. This chamber measures approximately 120 to 125 meters in length, 25 meters in width, and rises up to 35 to 50 meters in height, comparable to a multi-story building completely buried beneath the mountain. To create this space, engineers had to remove around 315,000 tons of rock. By February 2016, when the final rock masses were blasted away, the underground cavern reached its full dimensions, marking a major milestone for the project. But creating the void was only the beginning. Immediately afterward, foundation construction began on a massive scale. A dense network of reinforced steel frameworks was installed, combined with high-strength concrete to form the base for equipment weighing hundreds of tons. Over the course of more than a year, approximately 750 concrete pours were carried out, with a total volume exceeding 80,000 cubic meters, enough to build around 700 houses. At the same time, load-bearing columns and industrial crane beam systems were completed, enabling the lifting and installation of equipment weighing up to 200–300 tons within the underground space. From a solid block of rock, the turbine hall was gradually transformed into a precisely engineered environment, where every structure is designed to withstand loads, absorb vibrations, and operate reliably for decades. And it is here that massive machines will begin to turn, converting falling water into electricity at a scale that very few facilities in the world can achieve. After the turbine and generator systems were completed deep inside the mountain, the electricity produced could no longer remain contained within the underground space. It had to be transmitted outward and integrated into the power grid. This marked the beginning of an entirely new challenge, connecting to the national and European electricity networks. A 380 kV high-voltage transmission line, approximately 17 kilometers long, was constructed across the Linthal Valley, consisting of a total of 53 pylons, many of which reach heights of 80 to 89 meters, comparable to a building over 20 stories tall. This line serves as the backbone, carrying the plant's full capacity of up to 1,000 megawatts into the grid. However, building this system in steep mountainous terrain posed an immense challenge. Most of the materials, from structural steel to conductors, had to be transported by helicopter, requiring thousands of flights to install each component under strong winds and extremely limited working space. Every pylon and every segment of cable had to be installed with near-perfect precision, as even the smallest deviation could affect the entire high-voltage system. Once completed, this 380 kV line not only connects Limern to the Swiss national grid, but also integrates directly into the European power network, allowing the plant to respond almost instantly to electricity demand across the region. But for those massive machines to truly operate and generate electricity, all that power must be delivered through the most critical system of all, the penstocks. What makes this system remarkable is not just its scale, but its very construction. The pipelines have a total length of about 2 kilometers, with diameters reaching up to 4.5 meters. They are fabricated from steel plates, several centimeters thick, rolled, bent, and welded into large sections, then assembled directly inside the mountain. Each segment must withstand enormous pressure, with a hydraulic head of up to 630 meters, generating pressures of around 60 to 70 bar, equivalent to conditions hundreds of meters below the ocean surface. As a result, the steel structure is designed as a multi-layer reinforced system, combined with welds of near-perfect precision. The entire inner surface is coated with specialized anti-corrosion materials, reducing flow friction and protecting the metal against high-pressure water environments over decades of operation. At points of maximum stress, the pipe wall thickness can reach 30 to 60 millimeters, strong enough to resist forces equivalent to thousands of tons of water continuously pressing from within, as the flow speeds can reach 20 to 30 meters per second. This system does far more than simply carry water. It is a precisely engineered energy transmission network, where every pipeline must be strong enough to withstand pressure, precise enough to optimize efficiency, and durable enough to operate reliably for 50 to 80 years.